The next speaker is Nick Heaton from Cadence Design Systems, where he is Distinguished Engineer. He's going to present a summary of a DVCon panel on SoC verification challenges. Nick is an ASIC and EDA veteran, more than 30 years, and worked on a lot of design and verification of complex SoCs. He graduated from Brunel University in 1983, the first-class honours degree in engineering and management systems, and joined Cadence 15 years ago, where he's a distinguished engineer. He's located in Switzerland today. Over to you, Nick.
Yeah, not for much longer, unfortunately. Hi, everybody. So what I want to do today is give you some sort of a summary of a panel I moderated at DVCon India, where we got two really interesting guys to join a panel with. So Nimal is a DV lead for Qualcomm on mobile SoCs. Sukumar is a DV lead for Intel servers. So two very different markets, two very different domains of SoC. Pankaj Kakkar also joined, who runs an SoC solutions group inside Cadence. So he basically builds reference designs to test our tools. And what I wanted to do was really understand, do new SoC architectures demand new tools and approaches? And the actual recording of this is also online. So if you're interested, you can reach out and I can send you a link. So the first thing we did was really talk about what functional challenges, and a lot of this is no real surprise, but mobile, Qualcomm are facing cloud and edge, are really driving big data, lots of AI engines. Workloads are unpredictable, so they need to do a lot of traffic modeling to simulate video and audio before you really assemble the whole SoC. And performance validation for those synthetic workloads is important. Cameras, the number of cameras on a mobile device are creating huge data processing demands, and across all of this, coherency with all of these multiple engines, compute engines, coherency is just accepted that that's going to have to be supported and verified. So it's a big challenge. Intel, somewhat different, but somewhat similar as well in the server domain, that distributed compute is a good one, but it demands a lot of verification. And just doing bare bones coherency verification, this was seen as a very big challenge. Again, performance verification a challenge, power management as well, centralized power controllers, and how you approach the power management verification was a big challenge. The next aspect we discussed was the resource challenges. What resource challenges are you facing? Because obviously designs are getting bigger, the designs are getting more complex, the SoC level protocols and interaction of those kind of system level protocols. So you can think of coherency as a system level protocol. It's not one IP, it's across multiple IPs. We have a lot more of those SoC level challenges coming up. Security, power management are all in that domain. So obviously from a human point of view, what the guys brought out was that you need to define a bug budget, because you will, given the number of people, you will need to find a certain number of bugs, and you need to somehow budget what that's going to be. And simulation is just one of the tools in a big armory. From a machine resource point of view, they want to use all of the tools, and so formal hardware acceleration. So formal trying to get the bugs out earlier, and at the system level, we'll talk about that in a little bit later. But hardware acceleration is just a given. It really is essential for some of these bigger designs. And they're really looking for lowering the bring-up cost. So it's not just the operational cost, it's how do you get your designs up and running. That can be a major factor for some of the more substantial designs, certainly on hardware platforms. you need some kind of partnership between the IP and the SoC teams, and partnership between EDA and SoC. And 3D IC was really seen as a coming trend that's really going to push things even further, because you start laying down multiple chiplets, you have to do some kind of full system level validation. And, you know, if you just do things the same way, you're seeing, you know, what Nirmal said was they're seeing 2 to 4x the compute demands each year. And obviously they're not expanding their server farms by that rate. It's just unsustainable. So there has to be something has to give. So we then talked about new approaches and went through a few of the things that are out there, and maybe what things that may be coming. PSS, so portable stimulus standard, is one of the topics. Qualcomm shared how they were very early adopters of PSS. At the moment, it's mostly used for project-to-project reuse. They're not currently using it for IP to SoC, so there is still more productivity gain through IP to SoC reuse that they may be able to realize, but the methodology is still in the early stage. So there's work to be done. In a way, you can liken this to the early days of constrained random, and that methodology plays a key part in shaping the benefits you get from the reuse. For Intel, the description that Sukumar gave was that System Verilog had a huge impact on IP verification. He sees PSS as being similarly impactful for SoC verification, particularly constructing scenarios that need to go from architecture to RTL. So I think really what he was bringing out there is particularly things like performance, verification, validation. You know, architects will give you target bandwidth latency numbers, and what, you know, for various workloads, you need to specify the workloads and reuse them to make sense of it. They have a goal to have broad adoption of PSS, but it's still emerging across projects. From Cadence point of view, one of the key things is bringing test intent early as part of the modeling. So being able to abstract the test intent from the execution engine. So in other words, be able to create scenarios that will run on virtual platforms, run on simulation, run on hardware accelerators is key, because then you can have content ready for when the RTL becomes ready. And so that also implies portability across UVM to software-driven testing. That's one of the big values. From hardware platforms, obviously both of these companies are big users of hardware acceleration, and that security verification is one thing that's really emerging. Nirmal gave an example of how validating an always-on camera was a significant challenge, and that involved managing multiple engines. Hybrid also, where you're part of the SoC model is in TLM and part of it is in RTL, was also being seen as a very valuable vehicle. This is where we start talking, and it's interesting to hear Tim's presentation earlier about applications of machine learning. So Nirmal was focused mostly talking about how regression management is a place where ML can really play. And stimulus management, which clearly is what Tim was talking about, is a very useful area. Debug with ML, so improving effectiveness of debug. That's a huge area of a time-consuming area for most customers. Let me skip forward. So another question that was interesting is, does formal have a part to play in SoC verification? And the answer was, I think, qualified yes. There's some specific areas where Intel were using formal to classify the bugs so that they can reduce the amount of simulation they needed. And Qualcomm use it mostly at the SoC level for equivalence checking when they do late ECOs. There was a discussion about 6 or 7 years ago about the automated assembly of SoCs, and that, you know, this was going to be push button affair, but it never really realized. And we certainly from Qualcomm and Intel's point of view, this wasn't something that they expected to happen in the near future. So in summary, no surprise, huge challenges, they're significant and they're growing. Coherency is a pervasive problem, and it's going off chip, obviously, with protocols like CXL, C6. Chiplet to chiplet coherency is a standard kind of approach to disaggregating the memory and building much more complicated, powerful systems, but it creates problems for the verification engineer. Add to this performance and low power security, there are big challenges. Resources are always limited, and you need to be smart with your tools and your approaches. I think one of the things that came out of this was verification management is front and central to optimizing the use of resources, whether it's cloud versus on-premises, using machine learning to harvest data during a project or harvest data from project to project. And also PSS is becoming mainstream, applying use case creation to all of these various domains. And as you'd be no surprise to a lot of us, hardware acceleration is just ubiquitous and critically important, but needs innovative models to improve the ROI and bring up time. And as I said, if you want to go and listen to the full hour's discussion, I can provide a link.
Thanks, Nick.
I think I'm on time, aren't I, Mike?
Yeah, did very well. Thanks for catching up. Just one quick question on the it's on the chiplets. I presume the challenge there is to try and model a system of multiple chiplets. Is there a solution for that other than what the current simulations are?
No, there's no magic bullet. So obviously you can do chiplet verification with, so for example, let's say you're connecting two chiplets with CXL or C6. You can use VIP to a certain extent, but ultimately there is cache to cache across the two chips. That is not just interface protocol, it's system level protocol. So the only real way of doing that is to do full-blown chiplet to chiplet modeling. Now what you can do is build a partial model of the chiplet with just the IP that is involved in that coherent path. But that's extra work. Obviously, you need to plan that and say, I'm going to do a partial build and black box lots of other pieces of the chiplet in order to make it, firstly, run faster, but also not use huge amounts of hardware capacity.
Okay. Thank you. Thank you very much. That was very helpful, Nick. And yeah, again, I think what we'll do is provide the links to all the full papers after when we send out the after the meeting. So that was very helpful. Thank you. Thanks, Nick.
Sure. Thanks.